Hello, Sean. Hi, Andres. How are you? Hi, everyone. How are you doing?
Hello.
Hi, Paul. How are you?
Oh, I'm good.
Glad to hear you doing well. Okay, we'll start in a few minutes.
Did you send me that email you said you were going to send?
I'm still working on it. I just wanted to check to see if are you teaching CIS5 at your campus, or do you prefer to teach another class over there, or do you want to teach it at MVC?
Oh, I'll teach a class at MVC.
Okay, I'll go ahead and cue fall because you said that summer you're going to be busy. So we'll take a look at the fall schedule. I'll have everything ready by tomorrow and I'll send you the draft for yours.
Okay, I was asking because, I get so many of the emails, I get flooded with emails, and I was afraid I missed it.
Okay, yeah, sorry, I got a little bit delayed. I just turned in the summer schedule. So I'll have your fall schedule ready.
Okay, great.
Awesome, thank you. Hi, everyone, how are you? Please check out your notes and your assignment for today, and we'll start in a minute. Okay, so we have a holiday on Thursday, Cesar Chavez Day, so that's gonna take up the time for our lab. So I'm gonna push the lab back till next week. As you are enjoying your holiday, I don't want to give you additional work. So we are just gonna complete the assignment today. So let's take a look at your notes and your assignment for this week, Unit 7. And then I'll go over the assignment and the notes with you now. So the lab 7 will be pushed into Unit 8 and I'll modify the label for it. So that way it's not confusing, okay? So no class on Thursday if you just join. Okay, so we will start with Chapter 7 notes, and starting this week and onward, we will be working with multiplication and division in assembly. So we want to take a look at some example program. I pulled some of this from the textbook and the PowerPoint from the publisher. And then we'll expand on how we will be using some of the approach for multiplication and division. So according to the Chapter 7 notes, we'll start with assembly language. As you worked on your lab since week 2, you saw how LC-3 is used to create an assembly program. So assembly language really is a low-level language. We closely work with the instructions or your opcode to tell the machine what to do, right? We set up the tasks and the subtasks as we talked about that last week. And when you look at other assembly language, you would see going to be some similarity. We would start with the memory address. We will have instructions. So sometimes you have more instructions than what you normally see in LC3, but in general, you will have, your operators like AND or, and then you will have add, and we can use add for a lot of different things, including multiplication. So it starts out with talking about assembly language and it goes into assembler. So when you assemble your program, when you use your text editor and you save your file and you click assemble, the assembler is a program that turns your symbol into machine instructions. So what you have in the instructions or your opcode as add and not and so on, that will turn that into machine instructions. So when you use your simulator, you would see the 0 and 1s indicated on your simulator. So for every line that you write on your assembly program, each line contains instructions for the machine, and each line is allocated 16-bit, which is a word, okay? So it would start with the memory address that you originate, and depending on how long your program would be, right, we would extend our program all the way to the last line, which is .n. And in the case where if you fill, right, that will associate the memory address to the location of your label that you have defined and identified. So in ISA, which is LC-3, you would have these symbols and instruction sets that would represent your opcodes. So like we said, when we do a load, or when we do a store, or when we add values, immediate values, or add registers, we're using our opcode and operands. We are also using labels when you're using fill, or in some case we use string to be able to output, but mostly we would use a label to either create some kind of flow in the program, like how we would branch, or we would have a label to store some kind of values. So labels will always be associated with memory location in the case where if we fill. If we're simply using a label to branch, like what you've seen in the last two labs, those labels are temporarily used in the program, so it's just a way that we can control the flow of your program. Excuse me. So with the labels, we are able to have additional operations. So later on, you will see that we would use label as functions or subroutine. And in that section of your label, we will have additional instructions for the task related to that subroutine. So in the example in following, you have this, which is part of your assignment as well. And this program is to multiply a number by a constant 6. And unlike your normal program, this one originates at hex 3050, and that's okay. You can start your program at a certain location, but like I said before, we don't want to go too further down. So we can start at hex 3050 in this program. We are gonna load the 6 label to register 1, and normally you would see this to when we utilize the label. So we want to bring the address for the label to register 1. We want to load number to register 2. That's the next line. And after that, we are going to clear register 3. And so when you're getting ready to put values or use a certain register in a certain operation, we want to clear that. So the third line is when we clear register 3 by doing the AND. Then we would start the loop. And in this case, we're using a label called again, and that's simply just a label that how we control the flow for the program. So that's how we're going to implement our loop. And in this case, we have again. And what we're going to do is we are going to add register 3 with register 2. So recall in the previous line, we clear register 3, so it's initialized at 0. And register 2 is gonna have the number, right, that we loaded for the label. So, and then our destination register is gonna be register 3. Then we are going to count down. So as it loops, we have to subtract 1. So we're gonna do an add R1, R1 minus 1. Because we're going to loop 6 times. So after the first loop, right, it's going to count down. So that's going to be 5 left, and then eventually 4, 3, 2, 1, and so on. So it's going to branch as long as it's positive, and it's going to come back and do the same thing again. So we're going to loop until it gets to 0, and it's going to stop. And so it's going to go into halt here. Okay. So when you are multiplying, you're simply just adding that number multiple times. And so here, as we implemented the loop, right, we're going to keep adding until we no longer branch for the positive. So we're going to branch positive, it's going to come back. And as it reaches 0, it's going to stop the execution. Now, in the next part, this is a little different. I think you've seen block work before. Okay. So as you recall from C or C++, right? C and C++ is a strongly typed programming language, meaning that when you create a variable or a container, you have to give it a data type. Now that data type is gonna tell the compiler how much memory it's gonna allocate to hold the values for whatever you initialize for that variable or that container. So if I have int var1, right, that will be an integer. So it knows that it's going to hold the integer. And so therefore it's going to allocate the space to be able to hold the values as integers. Now, using that same approach, we have to think about how we're going to store our values and how our values can be large or small. Unlike C or C++, we don't really type our data, right? But we have to think about our data size in assembly language. So now LC-3 uses a word, which is 16-bit. But in the case where if you have a larger size, you have to think about how you are going to control overflow or how you're going to be able to allocate space to fit a larger value. Okay. So here we would represent number as a block word. So when you use a BLKW 1, that just indicate one block word, which is 16-bit. But if we want to have a larger location, we would need to change up this value. So you can say .blkw, and you can modify this value to be 2 or 3 or 4. So that way we can create a larger memory space. So this is how you can use a one block word, is to use BLKW and then you will put 1 here. Okay. So now, can I tie this to a certain location? I sure can, right? But in this case, it's just gonna section, right, one block word or one word for that number value. Then in the next label, we're gonna fill it with a hex 6. Remember that the program objective is to multiply the constant 6. So a hex 6 is equivalent to a decimal 6. So we can simply do the fill. Can I do this program a different way? I sure can, right? I can possibly add the 6 as an immediate value to a certain register and handle it that way instead of a fill. But when you fill it this way, what it's going to do is going to take this value and it's going to tie that to your label called 6. And as you recall on top here, what we're doing is we are going to load that label to register 1. So register 1 really reference 6, which holds hex 6. Okay. So you can do it this way where you would use the fill like what we've seen before in our lab. And then after that, we have the end. So when you look at this program, overall in assembly, any assembly program would contain some form of instruction. So that's one element. It also would contain pseudo op or your assembler directives. And you can also add comments. So these are some of the things that need to exist in your assembly program. Now, depending on the language, some cases white space is ignored, right? But in the program where you would use the location and set up your weekday of the week, right? The day of the week, and then you would use the value to output the day. You have to align things accordingly, and because the white space take up a character, right? That would represent. So if you are off by one space, it might cut off the next line and so on. So the white space between symbols, right, are specifically ignored. But when you're dealing with a string, the white space is important, okay? Because that string is allocated in one word, which is 16-bit. So it's going to treat whatever that's in between your quotation mark as some form of character. Okay, so even though we have null terminated, so it's using that N as an additional character there. So if you're using like a line carriage or something like that, then it's just going to bring it to the next line. Now, the white space between your symbols, like add and so on, right? Those are not going to be counted. So it's not going to look at that as something valuable. We know that our comments is going to use semicolon. So anything behind the semicolon or after the semicolon is ignored. So we can comment out a certain part of our program just to make notes of our program. And you've seen this before in the prior lecture, but just to go over it again. So your label is always optional. We would use it when it's necessary in our program. But the mandatory part is that you have to have an opcode like add, load, store, not, and, right? And then your operand. So your operands are usually registers, or it could also be register with immediate value like R1 and then hex 6, and then your comment. Now for the project in this class, I don't need for you to comment every line, but you should comment the sections to really indicate what you're trying to do there. So for the reserve symbol in LC3, we would see your opcode like your AND, your add, your load, your LDR, your LDI, and so on. So those are used, right, as your symbols to instruct the machine to do a certain task. Your operands are your general register from register 0 through register 7 in LC3. And we can also use immediate number. So the hex will be indicated with the X. The decimal is with the hashtag. For your label, we would use symbolic name, and that would be the name for the memory location. We would separate, right, our operands using comma, like what you've seen here, right? So for between your registers, we want to put the comma. And so the last bullet here, it talks about the number, the order, the type, and the corresponding instruction format. So our destination register are always going to be right after the opcode. And in the operands, you would have, right, your source registers or your source register and immediate value. Or in the case if we're loading and storing, we would have your destination register. And then in following, we would use after the comma, a label. When you branch, you would branch to a label. And in that label section, you would define the task that, or give it the instructions on what it needs to perform. Label should always be placed at the beginning of the line. So for example, we would use loop here, and you can put like this, okay? or you can put it next to it. So it's really up to you how you want to set that up. In the case where if you tab it in, it makes it a little easier to read compared to if you just align everything from the left. Okay, so I normally would use the tab after the label, and then I would write the additional instructions, right? Like, so my opcode and my operands. And we talked about semicolon using for comment. It's ignored by the assembler. It's used for us, right? Humans, developers, to understand the program. So you want to make it meaningful to your program. So like, for example, if you have a certain functions, you can set up your comment for that function. And so that way you would distinguish that function from another function, or that subroutine from another subroutine. So if you are restating, a lot of the times that can be repetitive, but we've done that through practice. So that way, you could see the repetitiveness, but from here on out, try to, comment where it would be meaningful. And so you can use comment to separate pieces of your program, like data, certain subroutines, and so on. Okay. Now, earlier it talks about the pseudo operations. I wanted to go over this before I start answering the questions because we can apply the concept. So pseudo operations do not refer to the operations executed in the program. Okay, like the ones that you see with the dot in the front, those are the pseudo operations. They are called assembler directives. And they are used by the assembler, but they do not refer to any of the operations executed in the program. Okay, so for your .org, right, your origination, that is just going to be following with the address. So we would use hex 3000 or some kind of address there. That's going to be where your program is going to be placed in the memory. And then we have a .n. Now the block word, we talk about that. That's going to allocate the number of words. So whatever the number that you put in after the .blkw, that's going to be the number of block words that it's going to create for storage. We have used .fill. So when you fill, it creates, right, a location for whatever you fill for that label. Sometime we would fill with the hex value. So we can initialize that value, which represents, the address, or it could be an actual value like what you've seen in the example. So it's going to create one word. So it's going to take 16 bits and it's going to use that 16-bit for the fill. And then we've used .strings. So that's going to use the characters that you place inside your quotation mark +1 because it's null terminated. Okay. All right. Any questions? Okay, so let's answer our first question. So I've used the example program that you see. And what we're going to do is we're going to break it down into pieces so that way we can understand how all of these pieces work together. So looking at the example program for A, I want you to identify the instructions or the mnemonics for the opcodes in the program. So those are really easy, right? We see add. Okay, so I put add. We see VRP, so branch positive. We see halt, which it actually execute trap in the back. And we see and right up here. And we also see load, LD, the rec load. Okay, so those are your instructions in the program. They are your opcodes. Now, halt is not pseudo operations, right? It actually stopped the execution, so it is an instruction. Then we need to identify your labels. So we have number, which is here, where we use the block word. 6, where we would fill. Again, where we would be able to use that to keep looping. So those are your labels. And just like any identifier, you can use numbers and letters, okay? But avoid using number first. So you can say again 1, again 2. You saw this when I did the Fibonacci program where I have FAB1 and FAB2 because it's FAB, right? FAB1 and FAB2, as I have to implement the conditions in Fibonacci. Any question? Then we look at the registers that's used. And in the last lab, I mentioned that it's really important that you track your register throughout your program. At a certain time, if you need to clear your register, you need to do so, right? And sometimes we want to keep the register having that same value throughout the program, so we don't need to clear. We just got to make sure that we remember what it's holding and how we can apply it to the later part of the program. Okay, so in this program, we use register 1 as we load, right? Register 2 and register 3 we use for the addition. So R1, R2, R3. Will there be cases where you use all your register? Yes, right? But we can reuse the register as, we can clear whenever that we don't need the value anymore. And in the case of R0, register 0, right? When you have an input, you want to move that to another register because, if you have multiple inputs, it's just going to come through register 0. So keep in mind that register 0 needs to be freed up if you have multiple input. And if you want to have an output, you have to make sure that you get whatever that you're trying to output to register 0. And before we output, we also need to ASCII convert, okay? Any question? Then the next part is we're going to identify a couple comments in the program. That's really easy, right? If you're looking at the comments starts with the semicolon. So you can pick any of these, like R1 keeps track of the iteration, or clear R3. And then at the beginning, you have the longer comment about the program. So a program that multiply a number by the constant 6. So in the upper division classes, for example, like the compiler class or another class in computer science, certain professor will expect you to have proper comments throughout your program, right? You always want to start with indicating what your program is about. And as I've done this at the beginning, of your semester in the lab, you saw that I put what the program's about, what kind of input, what kind of side effects. So keeping that practice is essential because a lot of the professors would expect that from you when you take some of the upper classes, okay? So we want to comment with certain sections that would be important for us to note. So I put down one of the comments is to clear R3 or R1 for iterations. Okay, so you can state a couple of the comments you found in the program. Any question with number 1, A, B, C, D? Okay. Number 2, tells you to refer to the image that's below, which we've seen in our notes. And you need to provide an example that contains all the components of the assembly programming, which is label, opcode, operands, and comment. Okay. So looking at this, that's really easy. You can even pull it from the example program. So what we can do is we can do something like this, right? So when I did this when I wrote it down for the prior semester. So your label could be anything that will be significant in that program. So looking at some of the things that we've used, right? We've used POS for pause, NAG for negative, number, loop, and then for your opcode, those are for your add, not, LD, ST, LDI, LDR, and so on, and also the branch. Sometimes you can also do a jump, okay, JMP. Your operands are your registers, your immediate values, okay, or it could also be label. And then comments, we would just add in what that line is supposed to do or what that section is supposed to do. So an example that I would use here is I have a label called pause. And that means that usually I would branch to this label. Then I can do an add, R1, R2, and R3, given that register 1 either have been loaded or have some kind of value. I'm sorry, register 2 would be loaded or have some kind of values. Register 3, same thing, those are the source registers. And we are gonna place the result in register 1. So R1 is gonna be R2 plus R3. So simply in one line here, we can see that we are using a label. We're using your opcode or your instructions. We're using your operands. And we have a comment of what that line is supposed to do. Okay. Or you can have something like this, begin, right? And then you can do like an LEA R0, and then you can say prompt. User. And so if I'm implementing a while loop to keep prompting the user, right, later on, I need to make sure that I unconditionally branch it back to begin. So it's always going to ask, so it becomes a never ending program. Okay. So in the case where if you keep asking the user to do this, and if you want an exit, you can implement a branch condition so that way it would end the program. Okay. Like in some case, I've seen this for students who take classes like C, C++, right? They would ask the user to select option 1 to continue and option 2 to end the program. And if they press 1, right, it would just go into the prompt. So you can implement it that way where it does exit at some point. Any question? Okay. So let's take a look at number 3. So I used the example and I modified it. And so here what you have is you have something similar to what you've seen in our notes. Okay. So instead of multiplying by the constant 6, we are multiplying by 3, which is the constant 3. So you have pretty much almost the same except for the label that's changed. You have a 3. I filled that with hex 3. And then everything else is the same. We still have the loop and so on. So using this program now, we are going to explain line by line what that does. So line 1, we're going to start with the origination address, 3050. That's the start of your program. This line. Okay. Line 2, we're going to load register 1 with the label call 3. So here we're doing a direct load. So the label is going to associate with register 1. Line 3, we're going to load register 2 with the label number. So at this point in the game, we should know what this program is supposed to do when we look at it. And if you struggle with this, right, make sure you see me in the office hours or, make an appointment so that way we can go through and also review your notes and do your assignments so you can learn or review. So in line 3, we simply load the label number to register 2 and recall that the destination is always next to the opcode. And then for the next part, when we do the line 4, we're going to clear register 3, or register 3 is, which is initialized at 0. Should say decimal 0. Okay, any question? So anytime you clear a register, you always want to AND it with a 0. And in the first week, we talk about when you AND something with 0, anytime that you have a 0 in the mix for the AND, it's going to come out, your result is going to come out to be 0. So that's why we AND there. Then next, we're going to move to line 7 and through 9, which is in the loop with the again label. So line 7, we are going to enter loop labeled again. And as we do that, we're going to add register 3 with register 2 and store the result in register 3. So we simply take the number 3, right? We add it with whatever that the value in number is. So if I have, 7, I simply take 3, add it with 7. I'm sorry. I have 7 in the number, and then for register 3, that will be 0. So 7 plus 0, that will be 7. And then I would take 7, add it again, right? So 3 times, so that will give you 14 in the second round and then 21 in the third round. So that's how we can multiply 7 3 times. Keep adding it 3 times. And that's one approach. Later on, we're going to do a lab where we would do the bitwise manipulation to do the multiplication. Okay. All right. So for line 8, we are going to add the negative decimal 1 to register 1 to reduce the loop count. So we're going to count down by subtracting 1 for line 8. And then for line 9, we are going to branch positive. So branch if positive, it will reloop, return to again label. And so when it is no longer positive, as we are subtracting 1 each time, when we get to 0, it's going to not come back to again, it's going to go to halt. And then line 10, that's going to be otherwise exit loop, and that will be your halt. Okay, so we simply just take whatever that's in the program and put it back into plain English. So when you do this in pseudocode, right, you should be able to break it down to the subtasks like what we talked about last week, and then be able to type out each section of your pseudocode in assembly. So when I build a program in assembly, what I do is I take the pseudocode, I copy and paste it in the text editor. And for each of the line in the pseudocode, I would start filling in my assembly program so that way I can track it. So, you know, that has always worked for me, but some of you start coding first before you do pseudocode, and then you have to make adjustment throughout. And that can be challenging because sometimes you have to scrap your entire program and start all over again, and you don't want effort wasting. Okay, so you can start with the plan and write out your pseudocode and then start filling in the section. So when you have, you know, if else statement, like if do this, you can start thinking about branches, and then you can just put that in and make edit to your program. And then at the end, you can comment out the pseudocode part, and you should have a whole program. And then for C, we are going to look at line 13 and 14. So that's the fill section and the data section. So for line 13, we're going to allocate one block word for the number label. And then line 14, we are going to fill, I should put fill label 3. That's fine. Label 3 contains hex 3. Okay. Any question? So here all together, right, we have line 1 through 14. We should be able to understand each section. Now, as we progress, later on, we're going to start working with stack and subroutine, and we would jump back and forth in the program. So the program will get longer and it will get more complex. And as you do that, you know, sometime when you need to store the value back into the address space and then load it later on, and so on. So you will have more complex program down the line. Question? Okay. So here, this is a program that you did for the prior lab, 2 labs ago. And using this program for number 4, we are going to identify your assembler directives. Okay. And remember that we define assembler directives in our notes. Those are the one with the dot in the front. Okay. So first off, the first line, we have the origination. So that's 1, right? We have dot strings, that's 2, dot end, dot fill. So those are your assembler directives. And you also have puts, getC, and halt. Okay. As you see here, we have the puts, the getC, and the halt. So on this one is really easy. We would identify your pseudo operations or your assembler directives. Okay. Now coming back to the notes, it talks about that here. The pseudo instructions are halt, in, out, get C, puts. Okay. These are used, right, for various things, like for input, output, obtain a character, display, right? So when you're using a halt, we're using trap vector 25. Make sure that we know our trap vector for final exam and quizzes. So when you simulate this, when you run the program, if you look at your simulator, it usually indicates the trap and its vector on that line when you're using the pseudo instructions. And pseudo instructions are slightly different than your regular instructions, which are your opcode like and, not, and or, and, not, and add, or load, okay? Because it uses trap as an instruction in the back. When you're using an in, that's a vector 23. So it uses register 0. Out, it's a vector 21, also uses vector register 0. And then get C, also use register 0, that's vector 20 for get C, and for puts vector 22. The way that I remember this is out is before puts, because that's vector 21 and puts is vector 22. Get C is before out, and then in is 23. Halt is later, so that's usually an execution, so that will be 25. Okay. So you would have the vector closer together for the main purpose, and they design it that way, right? So your out and your put, that's really displaying. So you have 21 and 22. And then for your in, that will be 23. And in is different than your get C, because get C reads one character from the keyboard, and in it reads one character from the keyboard, but it prints it onto the console. Okay. Any question with trap vector? So that will bring us to number 5. Identify your trap vector in the program. Okay. So what do we have? We have these, right? So let's do that. So halt, we know that it is trap at vector 25. And then if you're not sure, you can always go back to this table, right? Your get C is 20 and your puts is 22. Yeah, so just those in the program for that's below. right? Puts, getC, and halt. Any question with number 5? Okay, so let's look at the notes for 6. So the authors of the book gives you some tips on how to work with LC3 or assembly. Okay, here's some of the style guidelines, right? Guidelines are not mandatory, so it's just suggestions or recommendations on how you should apply the style when you program. And we want to think about best practices and how we would write our program and make it, the readability of your program should be there. And, and as you go through the iteration of building your program, sometimes, it doesn't look as clean at the beginning. And as you improve it, right, it gradually becomes better. But for the style guidelines, you should indicate author's name, date, purpose of the program. So whenever I grade a project and then when I look at your GitHub, right, I expect that in the README file. Many students just put like final project, right? What is your final project? Because GitHub is designed for you to share your source code with the larger community. And possibly it could be potential employers or, colleagues that are looking at your repository. So we want to make sure that, leaving our CCD, you want to apply not only the learn concept, but the best practices so that way you can be ready for the field and the upper classes. Okay. So we want to put in the information who created this. And when you look at other developers program on their GitHub repository, right? Usually they would say something about copyright, but it's important to make a note of your date and the purpose of your program. Okay. Then when you start working through your LC3 program, right, we would start with labels, opcode, operands, and comment. And we want to align it so it's easy to read. You can use your comments to explain or track your registers or the purpose of that section. Okay, so your comment should explain, right, the purpose of your instructions. When you're using labels, symbolic names, right, you should make it meaningful to your program. You can use upper lowercase. In LC3, that's, most of your simulator and your editor for assembly, right, not case sensitive. We normally use all caps because that's the practice, but you can mix them up like this, ASCII to binary. You can also use letters and number. And then we talked about having comments between sections. And don't try to, because LC3 instruction is really short, right? Or your assembly instruction is short. So you shouldn't have a very lengthy line for instruction, but for your comment, right, we don't want to have it wrap around or make it too lengthy. So we want to make sure that your statements are aesthetically pleasing, so it looks clean and it's easy to read. Because not only for you, but for others who are accessing your source code. Okay. So we can include those things. You don't have to put everything down, or you can just copy and paste over. But keep in mind that these are the things that I will be expecting for your final project or your project. Okay. And make sure that we allocate time for your project so that way we can touch up our program, test our program, and making sure that things work. And I will release the project in a couple of weeks. The project is gonna be a team effort. So you can work together on the program. In the past, many of my students, they divide up the program into different sections, and that will be good because that way you can collaborate and improve certain area or expand on certain area. Do not rely on one person to do all the programming, because if that person doesn't have anything as an output, then your team will suffer. Okay, so try to piece it out to smaller chunks and then work on it together. Any question regarding 6? And you can find this on page 4 of your notes. So in the text, it talks about, how we can use an example program. This program counts the input characters in a file. So what it does, it reads the file and it counts up the characters. So as you take a look at the flow chart, you would see that we would have a start process, right? Where it would prompt the user and ask the user to input. And as you notice on how they use this flow chart, is that they put in the registers and also your pseudo operations. Okay. And so when you create a flow chart for your project, you have to think about, how you can use that flow chart effectively. Okay. So as you have these pieces, you can put in your registers or, the instructions that you need. Okay. Any question with this? Okay. Now, particularly for programs that my student turn in, doesn't matter which language they turn it in, Python, Java, C++, LC-3. When I look at your pseudocode and your flowchart, I particularly look for, how you approach it, and also if you have the proper branches. Okay. Many students, they just do like, they would say if statement there. I don't know the conditions for the if statement, how it branches. So you got to make sure that you think about that, because those are all also, right, processes or sub-processes that the processor needs to execute. So make sure that we apply the branches properly. Okay, and I will look for that for when I grade your project. And so when you put it into LC3, the program would look like this. And we will work with pointers down the line too. So what you can do in C or C++, you should be able to apply that in LC3. And the way that you see that here, they load a pointer with as a label. So it's going to point to the characters, right? So we clear register 2, load PTR to register 3, obtain the character from the user, okay? And then see how they do the LDR here. So when you're using the LDR, notice that you can load the immediate value to the register and then put it on register 1. Okay, so register 1 gets the first character. Now, later on, you're going to see that it needs to ASCII convert. Okay, and then do the test match. I think this program is missing the copy. So there should be one more line where it would take whatever that comes in from register 0 and put it onto register 1. Okay. So down here, you would see that they do the add and put it onto register 1 to do the match. And then if it's no match, then they're going to keep going again. So the example shows you here that it still goes through the conversion process once it comes in and then before it actually output. Okay. Now the way that they use this is they use a label and they have another label to be able to get certain character for match and then test it. So for the next character, they just have it go to another label. Okay. So that makes it a little better to debug in the case where if you need to fix it. And also you can distinguish between the first character and the second character or the next character. And it's really to the developer preference, in my opinion. So assembly process. When you write your program and you click the ASM button or assemble button, what it will do is it's going to have the first pass. What it's going to do is going to create a table that contains all your symbols, including your whatever. So whatever that you define in your program as labels, it's going to create a symbol table. Then that it's going to use that symbol table and go through a second pass. And after it goes through the second pass, it's going to create your object file, your OBJ that you've seen. That's how you're going to be able to simulate. And so here it walks you through the actual process. So when you save your .asm, how does it get from an ASM file to the OBJ? We talked about how it creates the symbol table. So it would start with your origination statement, which is the first line in the program. And that would be the first address that would be used for the first instruction, which is the next line after the .org, right? After the origination. So in order to track it, it uses the location counter or the LC to really track which instruction is current. Now on the lines that don't have a label, okay, it adds, if the line contains a label, then it adds the label to LC. If the line that doesn't have a label, then it doesn't need to add anything to the symbol table. So as you have a label, it's going to put that onto the LC so it knows what instruction is current to that label. And after that, it's going to increment the LC so that way it can track the next label. Now, when you're using your assembler directives, like block words, strings, it increments it by the values that you set for the block words or your strings. So that means that if I do a .blkw3, it's going to increment that by 3 because there are 3 words or 3 16-bit word size for that location. In the strings, it depends on how many characters you put inside the quotation marks, and it's going to do a +1 for null terminated. So if I have a short string, it's going to increment the word, right, based on that 1 per character. So if I say hello, right, HELLO, HELLO with the null terminated, so that will be 6. So it's going to increment that by 6 because it's null terminated. And then when it gets to the .n, it's going to stop execution, right? That's it for the program. For the second pass, since it already create your symbol table, it's going to convert that to the machine language. Now in C, C++ or Java, right? Or let's just focus on C, C++, the compiler handled this, okay? A lot of the things that we do, the compiler also handles. So in the second pass, the information that was placed on the symbol table, it's going to convert that to machine language. And if things are executable or they are operation, then it's going to generate the appropriate language instruction. If your operand is a label, it's going to go back to the symbol table and find the address. So the symbol table is a list of your label and the associated addresses. Okay. We're going to come back to this concept later on when we talk about stack. Okay. So hopefully when you look at this, you would visualize it. And so when you look at the simulator, right, how does it know what to place on the simulator? It's really because of this design. Now, in the case where if you have inappropriate statements, like we're trying to add a register with the label and put it onto the register. Okay. Or when we're doing like a not R1 with the decimal, right? When you're doing a not, you should do a not register itself, right? So it should be not R1, R1. But when you're doing it this way, it's inappropriate. So these are some of the potential issues, and sometimes it just, oversight, or, if you're trying to do things quickly, you're not paying attention to some of the areas that could potentially be a problem. We cannot use not with an immediate value. And this, it's going to throw an error because it doesn't have the second source. Okay. So when you debug that, and sometimes even if you write it out properly and if your values are inaccurate or it's not looping properly, you have to go to, logically, we have to think about the section we need to troubleshoot. If it's not branching properly, look at the line before or the few lines before on how we are operating in order to get a value to branch. Okay. And if it's not looping, it's not setting it to the branches. So if we troubleshoot that, look at the look at the label section where we branch it to. Okay. And we've seen this in our lab when you have a very large value. Remember that there are only 5 bits and 5 bits cannot hold this. So if you're using an immediate value, make sure that it fits in those bits, okay? And if it's not, we have to control overflow. So we have to allocate an additional memory location for anything larger than that size. So here it tells you that when you have an address that's associated with the label that's more than 256, it cannot use the PC's relative addressing mode. So you gotta stay within that 256 area. Okay. Okay. Then on page 7, it talks about what files it's generated. And you've seen this when you click assemble. When you create your ASM file and you have the assembler, which is the program, right? After you click assemble, you will have the assembler. It's going to create a .bin file, which is your binary listing. This is what you also see on the simulator. It's also going to create a .hex file that's going to be your hexadecimal listing. It's going to create an object file, your OBJ. This is what we use for the simulator. And earlier we talked about the symbol. So now you need to look at your files. You should see a .sym for the symbol. And that's how it's tracking your label. Then lastly, it also create a .lst file. That's going to be your listing file. Okay. So coming back to your assignment, what type of files are created in LC3 after you assemble? When you save your file, you need to save it as a .asm. Now, if you're using, right, other language, for example, like Microsoft ASM, okay, you should still use .asm. So when you save, it should be a .asm. After you assemble, it's going to create .bin, .hex, .sim, .list, .obj, .object. Those are the files. And each of these have purpose. So for B, the type of file that's used to simulate an executable image, which is your OBJ, right? That's what we load in our simulator. And for C, in the assembly process, your program labels and addresses are managed in symbol table.sim. The type of statements that would require increment in the LC during the assembly process is your block word and your strings, .blkw and .strings, stringz. Any question? Okay. So for number 8, these 3 statements they are operation and data movement statements. But because they're using immediate values, so when you look at those values, automatically you should say that they're large. Okay. How do I know that? The decimal value 300 is larger than 256, so no. Okay. So the simulator, the assembler, when you assemble this, it's going to throw an error. Okay, it's going to tell you immediate value is too large. So how do we fix that? What can you do to fix it? Like what we did in the prior labs, right? We broke it up into multiple instructions. Remember how we were able to add or subtract 48? Well, we can break it up into multiple adds, right? We can have multiple lines that would keep adding values. Eventually, we will get to 300. Okay. And the same thing for B. Immediate value is too large. So how can you subtract 260? Well, we can break it down into smaller value, and we just have multiple lines to add to yield that negative 260. For C, when you're loading with a value, so this is an immediate value, and load it to register 2, this is not a label. What you can do is you can think about how we can use the label and do a fill. And if it's still too large, which it will be, what you can do is you can think about how you would be able to make it into multiple locations for the overflow, or instead of, because we just need to get this value to register 2, we can also revert back to the previous approach that we talked about, which is adding multiple times. Okay. Any question? In the Windows environment, and most of you have experience in using Windows PC. When you're using LC3 assembler, the files that should be generated is a .exe. So when we write the program, it is a .asm. You have to package it. For Windows environment, you have to convert your file into a .exe. Now, the modern assembly language, LC3 is really designed for you to learn because it's simple. But when you're working with other assembly language, you would see that it would use your C compiler. And you can use things like Visual Studio or anything that would have C compiler. So in the Windows environment, if you program in that, you would use the C compiler and you would be able to package it as a .exe. Because to run that program, the user needs to click that executable in order to launch. So I can have an application, that would just, let's say, multiply 2 numbers and would ask the user to input. When I write it, it is in assembly, but in order to release it for beta testing and also for launch, right, for deployment, I need to make sure that it's packaged as exe. Just like how you write a program in C++, that's a .cpp. But that program can only be ran if the user have a compiler, right? So we want to make it where the OS actually understands, right, the instructions of what our program is designed to do. So we have to package it as an exe for the Windows PC user. Any question? So it doesn't matter which language you write, right? Like C#. Often you would see C# is used for Windows-based applications, but you can definitely use other languages, as other languages can be cross-platform. So if you are creating applications that will be native to that OS, like Windows, then we want to make it executable. Okay, so let's talk about LC-3 object files. So when you assemble your program, it creates the OBJ file. And in that file, it would start with your address, your origination address, as is illustrated here on page 7 of your notes. And then following that, it will just be additional instructions, right, that you have following, starting with the first instruction. So if we're clearing register 2 in this case, that will be the next. And then we load the pointer, and then we have a trap for input output and so on. Okay. So here, what you would have is your object file is not necessarily a complete program. And in our case, we use our object file to simulate our program. So in that, what you would have is you would have routines that the system provides for specific instructions that you include in your code block. So in some case where if you divide up your program to multiple developers, they can create smaller programs and use them as a modular approach to give you a larger program. And you do see this in the aspect of today's world, right? We can incorporate, like for example, in my Python class, they can use modules, programs that already been written by other developers to be able to launch a brute force attack using Python language. Okay. Well, we don't have to start from scratch, as we already have these open source tools that's available. And similarly, you would see that in assembly. You can have multiple programs that's created by multiple developers that will be able to give you the larger program. So when I taught this class with Microsoft ASM, what we did was they have to create a project with an interface, because for Microsoft ASM, they can add buttons and, you know, lists and menus and things like that with the interface. It is a little bit more user-friendly as far as how the program interact with the user. So instead of doing it from scratch, making the buttons manually, what they can do is they can incorporate library routines that were created, and they can simply add their own program elements and an objective to with that library in order to use. So they would use a .external to bring in some of the external library. And that's how assembly works, is that you can use additional library just like how you would do include, right? Or using a .h file in C. Okay, your header files. So here it talks about how it would be able to load multiple object files. So in the case where if you're using multiple OBJ files, it's able to do that. And it's going to start executing at a desired address. So if you think about like Java or Python, right, we would do an import. We can bring in packages or modules. And what it will do is it's going to start at a certain location in the memory. That's where the program is going to begin. Whether it's higher programming language, or in our case, assembly. So in the object file, it's going to start at a certain address. And then it's going to load, right, the program in that subsequent location after that starting address. So that's why we always have to have the origination. And it would load your program in LC3 between hex 3000 and the end of the array, which is FDFFF. FDFF. That's the end address. So we have to be in that range. And we don't want, in the case if you have multiple object files, you don't want to overlap. So you have to think about how those files are to be used together. Because if you have overlapping, right, that's going to create problems and it will not work. So when you load, what that happens is if you're using multiple object files, it's going to copy the image, right, of the OBJ, which is generated by the OBJ into the memory. And so it would fit it based on what's available in RAM. And then after that, it's going to adjust based on how it's going to load and store the addresses. And this is what, at the low level, your processor does this. So earlier I mentioned that you can use things that are external. And when you're using C compiler with assembly outside of LC3, you have to set up your IDE to link to a certain library or files or packages. So when I teach Python, we use a lot of the things that are external to the Python package. Okay, so for example, in my class this week, they have to use a library to deal with FTP. Okay, so PyFTP or another library that would deal with SSH, which are protocols for servers. So they have to first bring that into the system. So you cannot link or use things external that it cannot find. Your computer is very simple. In order to link files and packages, you have to bring it in, meaning that you have to download it and install it so it could see it. Then after that, you would tell it through your code that it is an external component. Now, if you don't download and install it, there are ways that you can link it through a path, and depending on where that is, okay? So you can point to a certain location. So because these object files are independent from one another, you have to make sure that they see one another, okay? This is a harder concept in the sense where on the low level, right? But if you think about like how we use Java or Python or C, C++, anything that you use, it has to be in that same directory or a working directory. Just like how in your IDE, you have a source folder and any components that you want to utilize has to link to that source folder. So you have to set up your IDE to be able to see it. Okay. And if it's not there, make sure that you somehow associate that with your system variable and path. Otherwise, it will not execute. So with that, when you're linking, it's going to resolve the symbol for the other files, right? Like the library that you're using outside of what you have. It's going to bring in those symbols and it's going to tie those symbols to your program at the assembly level. So when you're using the .external, it's going to tell the assembler that the symbol defined is in another file. Okay. And if that file is not found, it cannot resolve those symbols. It cannot put them on. So it's simply going to copy those symbols and put it on the actual program, your code, the symbol table, so that way it can associate that. Okay. Because if it cannot find it, it will not be able to locate the label or the instructions from the other program. So here it talks about the linker will search the symbol table of the other modules to resolve it. And it's going to complete by generating the loading. Okay. And if you're using like ARM or another like NASM, if you're using like C compiler to build your assembly program, you can simply use in Windows, you can use Visual Studio, and then you just have to set up the link. Okay. And as long as the files exist in the system, you browse to it and you won't be able to link it. Okay. But if you found a library on the web and you don't bring it into the system, it will not be able to connect it. And so that was some of the challenges that I saw when I taught the other type of assembly language. And in this class, we don't use so much external. I wanted to expand on it a little bit. So in the case that if you work with it, you know how to, at least you know the processes that's involved in it. And you should always read their documentation. They usually tell you, right, how to utilize their library or their source code. Okay. Any question? Okay, so the linking is simply to resolve symbols for different independent objects. So for 11, when we are loading and linking in our object files, loading means that it's copying the executable image into the memory. Linking is to resolve symbols between independent files. And for number 10, I put down to see page 7 of your notes. So some of the tips when you're loading multiple object files in assembler, you can go to your notes. And it tells you here. And here. So it's important to make sure that we think about where we're going to load. Okay. From the origination address, and that's your ending address. So the beginning, this is in LC3, that's the first, right? 3000 is the top, and the end is this. Okay. So we don't want to use overlapping object files. So we don't want to overload that overlapping. Okay, so highlight some of those things and you can put that down for number 10. 7 and 8. Any question? Okay, so again, there's no class on Thursday. It is a holiday. So I hope that you enjoy Cesar Chavez Day. As you know, this is only the beginning of the week, so you have a couple of days, but I will not hold Zoom session on Thursday. It's a holiday. If you have questions or any concern, you can address it via message. I should be able to respond to you. And, or you can come to office hours. I won't hold office hours on Thursday, however, but I will be available Wednesday. And if you need to make an appointment, I am also available sometime this week, but not Friday. I'm going to visit LA Community Gardens to set up the living classroom and MVC. So we need to do some research on that. So, but you can send me a message. I should be back in the evening. So if you want to meet, then we can set up something there. Okay. All right. I'm going to stop recording. If you are finished, you can turn it in now, or you can submit it by Sunday.